Should we just get going without all the other ones? The other 7. What we're going to do. All right. It's actually going to be a short lecture. It's just about preparing the project, and you guys get going again and do homework and projects. This is really what you need to get going. Any questions from your side concerning working with the simulator, getting your homework free done? Good. Not waiting long. Perfect. Everybody has everything sorted out. So I just want to tell you for a minute or for most likely 30 minutes about the project which I outlined a week ago, and now just doing it a little bit more carefully so you have all the information you need. It requires homework 3, so it's built on what you'll hopefully finish today. So the idea in the end, as I mentioned the last time, is to make the NAO stand on one leg. And what does it take? And we'll focus on the simulator. I think getting it on the real robot, from what I can see, will most likely be something which we can do optionally, not with a deadline. So getting it done in simulation will be, I think, the most achievable thing at that moment. But if you get it on one leg, you can do fun things. You can actually, it's a very little step forward, as you may hopefully have seen in homework 3, to go from one behavior to a sequence of behavior. All what you do is essentially a switch statement, and you cycle through multiple behaviors one at a time. So if you have if you know how to stand on one leg, that means you go over, lift one leg up. Well, it's not very hard to put your leg back down, go to the other side, lift it up. And if you wanted to, you walking. So. Yes.
So while doing this, don't we have to consider the gravity?
I will talk about the constraint in a second. What really goes into doing it mathematically correct. So there's a crummy way how to do it, and there is a mathematically correct way how to do that. So I think I will answer it in a few slides. Okay, so let's just jump into that and look at what it's supposed to look like. Here we go. So this is your NAO, and this is a reasonable way how it can be standing on one leg. Where you can actually, from this posture, you can actually see a little bit. So similarly, you need to move your ankle to the side, and you move your hip. And these are actually the 2 key components which you have to work with. And then you have to pull the other leg up. So fine. Let's look at some of the important components. You need to know the NAO degrees of freedom. And I have a slide here in the next slide, which will hopefully make this clear. So the best thing is to start the NAO simulator. Initially, the robot's in what we call a free space state. That means we hang it at the 0 point of the world coordinate system. So it's not touching the ground. And the good thing is you can move it freely. That's the mode you've been working with right now. On the NAO task process, if you type there, there's a few useful commands. Let's put it this way. The most useful one is on every of these processes, to do the old-fashioned Unix command, which basically lists all possible commands that you can use in the interface. There's about 20. It's not that many. And then one of the very useful commands for you to use is the where command, which will simply list you all degrees of freedom, where their current position is, their current velocity, their current acceleration. Okay? If you do that, you see all these degrees of freedom. You see they have numbers and names. I'll tell you in a second what the abbreviations and names mean to make it a little bit easier. You care primarily for the project about the leg degrees of freedom. You do not really care about the arms and head at all. So these are the key leg degrees of freedom. I'll show you in a second one more time, but just, okay. Flexion extension, these are the kind of biomechanical names. So hip flexion extension is very simple. It's this motion here. Swinging my leg at the hip. Then hip adduction, abduction is swinging it outward. Knee flexion extension, well, not very different. There's only one thing you can do with your knee. Anything else you do with your knee means breaking the knee. Ankle flexion extension is ankle up and down. Ankle adduction, abduction is the side movement, which you notice it's pretty impoverished in this human, so we don't do too much with it. And the same is for the right and for the left leg. That's all there is. So it will be very straightforward. And you can basically try this out on the NAO by basically saying, where is this? There is the go command. So again, another useful command. Now.task go. And it will ask you, do you want to adjust all degrees of freedom or just one? You can choose all, then you have to go to all 26. This might be excessive. Or you just choose one, which you want to choose, and you have to use the numbers, which you see here. And I'll show you the numbers on the next slide one more time. And I could simply say go, and then I type 20, and then I can set a new desired position for the hip flexion extension. And you can try this. You change it a lot, the robot will fall over right away. That's most likely what's going to happen. So you can do this very carefully in small increments, but you can adjust the desired position. You can do this much more nicely with the arms, that will not make the robot fall over easily, except if you put your arm far out, it may actually fall over, because the center of gravity moves forward and boing, you go. So you can basically play with this and see a little bit how the degrees of freedom move. If you're in free space, it's nice since you can also move the legs without falling over since the robot is held. You can always toggle back and forth between free space. You tap it once, the robot gets free. You tap it again, it gets basically jumps back to the zero coordinate system and continues. Okay, if you want to adjust the view of what you see in the graphics window, it has a very simple interface. You just click on it. You get a pop-up menu, and it shows you all the commands there is and a keyboard shortcut. It's a very trivial keyboard shortcut. So it's using some of the normal H, M, J, whatsoever keys, how to rotate it and do things. Okay, so that's essentially how you can play with a simulator and explore a little bit if you want to see what's going on. Sometimes what is important to know is what is positive and what is negative in a movement, and you have to make to try this out. So just from old definitions, when you move adduction, abduction to the side, we call this actually, this is the negative direction. This is just because of competition which we had in robots for the last 15 years. Most of the time, so flexion extension, the knee goes in, this is positive, it collects it, flexion extension forward is usually positive, the same as for the ankle, upward is positive. Most things are pretty obvious. But if you don't know, just try it out in the free space position and you know what's positive and what's negative. Is the picture of all degrees of freedom as we call them. Now people call them differently. They use very strange names from my point of view. So we stick with what I just told you, and the simulator is using, and this is trying to basically point towards all the things one more time so that you know what's going on. Okay, yeah, the resolution. It's a little faint in the background, but again, let's just go on onto the things which we have essentially 3 degrees of freedom here. What's this? There's a weird degree of freedom in the NAO, which is the 4-bend degree of freedom. This can do it like this, but it does that when you do that, and I would recommend not to use it. It actually, it's a tilted axis. Actually, the legs have to go further apart while doing that. So it's when it does that, it actually spreads his legs like this. And if you go back, it puts them back together. So that's a strange degree of freedom. You don't really need that at all. It will just make you fall over. Again, what matters to you are these 5 flexion extension. Basically, is forward. This is the rotation axis. The green thing, the red thing is the rotation axis for adduction, abduction. You can see it will be rotating forward. Then the knee is clear and the ankle is pretty clear again. Okay, and you get the numbers and the names, and also a slightly longer name is generated. Okay. So, what should you be doing? Just giving you a very simple scripting outline. So you want to stand on both feet initially. I'm not sure whether you need it. Maybe you have to go a little bit down in your knees, but I'm not sure whether you need that at all. It could just be. Then you basically have to move the center of gravity, or actually the projection, if you remember now. So when you have the NAO simulator, it's a very funny way of drawing the simulator. So you get this nice red ball here, which shows you the projection of the center of gravity or the center of mass. It's the same word, well, not the same word, but the same thing. Center of gravity is somewhere, most of the time it's here. And its projection downward to the walking plane is the red. And what you want to do is to move the red ball to 1 foot by moving most likely this degree of freedom, this degree of freedom, this degree of freedom. So this is the, do the right thing, this is left hip, adduction, abduction, right hip, adduction, abduction, and then the right wrist. The wrist is an ankle. Ankle, adduction, abduction, left ankle, adduction, abduction. Okay? These are the most important things you're going to do. So in theory, you want to move. If I want to get the center of gravity to this point, so under the foot, I need to change this one a little bit in this direction, and the this goes over there. This one has to move somehow a little bit. So this should hopefully do it. And you can think of it essentially as some kind of a parallelogram which goes from here to here. That's kind of the key idea. After you have your center of gravity under the foot, in theory at least, you should be able to lift the other foot up. And I basically told you just move over the right foot. I had to choose something so I can write it explicitly. You can also do everything with the left foot first. I don't care. I just had to write about something. So the left foot up, that should work, and then you should be balancing, and you're essentially done. And then if you get carried away and have fun, you can put the foot back down, go to the other side, since it's just copy and code at this moment, and put the other foot up. And then you can do it continuously back and forth until you die and see whether it falls over at some point. Or if you get aggressive, you could actually, when you put your foot down, just basically stretch your knee a little bit more. It's going to be maybe a little more complicated. Maybe it's easier to go backward, actually, since you cannot overextend your knees easily. You could move your hip movement a little bit forward. And that will set a little bit of it. So one of the problems it was most like, if you put your foot back down, you want to make you want the foot to be parallel to the ground as much as possible. So if you start to create a very tilted thing, then you fall over more easily. Because you're just touching, like stepping just on the edges of your foot sole. Okay. Good. So this is kind of the outline how to do that. What is it what you will need? You want to do a smooth movement in whatever you're doing. So the minimum jerk thing, which you've been programming for the homework 3, is really useful for that. Degree of freedom for every direction, whether it's x, y, z, for every x, for every y, for every z in a Cartesian space, or for a joint space. It's the same function. It just creates a very smooth movement. And smooth movements are good, since they avoid that you fall over easily. And using the inverse kinematics controller from homework 2, which we also did for a center of gravity, is actually a useful thing. I'll show you two ways how to basically do the homework. I mentioned that the last time. I'll have it a little bit more in detail now. So there is a way how to avoid that. It's a little bit more of a hacky way, but it may make you happy if you're under total time pressure. You're grouped now. All this is done in groups. Remember, you can do this together, have fun, drink some wine or beer, or no, don't do that. Drink grapefruit juice, not too much sugar. Cranberry juice, that's good, organic. So that is a drink. And you can basically then twiddle things, or you can have also multiple approaches in your group and get it going, whatever you like to do. In the end, what we would like to see is that you should show us the simulator going from a full stance on 1 foot. And that's all. Then the project is done. So it's a very simple test, but it's kind of nice to see all the little things which come together to make it work. Yes? I will say that in a second. No, I do not expect you to do that. Oh. Approach, so that is the hacky approach, which is very manual. So what you have to do essentially is you basically use freeze base to put the robot on the floor, and then you use the go command to do very small increments to change the posture of the robot until you get the center of gravity over the foot. Now, it's important, okay, if you are, remember, you're dealing with this thing which looks like this. So this is a loop dynamic of system because we assume we don't slip. We will slip sooner or later if you do something too bad. But initially there's enough friction that you don't slip. So if you just say, I'm going to move this degree by itself outward, but it's not going to work. It will try to do something, so it will actually move its hips somehow. But now you don't do this in a coordinated way. Coordinated way in this case really means you need to simultaneously give a command to this, to this, to this, and to this degree of freedom. Otherwise, you will create tension. It's like you're putting forces in that nice little parallelogram. So if you use the go command, so we're back to this guy here. Now you can basically go, and if you use option 0, you can change all degrees of freedom at the same time. And then you would go, let me see, if I manage to go backward to my little picture. So you would use 21, 24. Let's do this. So we need degree 21, 24, and 18, and 14. And use this go command and change these things all the same amount. So it's very simple. Let's assume we want to move over by 0.1 radians. Everything is in radians. If I want to move this here by 0.1 over, so in this degree of freedom, 0.1, it will actually move us a little bit in this direction. Then this here has to do negative 0.1, since it's mirror symmetric, it has to go out a little bit. So in general, degrees of freedom are a little bit done in terms of the sign convention. You have very big eyes over there? It's okay? Good. Fine. Just checking. You get a heart attack? Let me know. So minus point. So basically, what is positive in this direction is also positive in on the mirror side. So that if I want to do something which goes here and this here goes in the other direction, then this here is positive and this is negative. It's not mirror symmetric anymore. So fine, I move that over. Now the ankle adduction abduction. What's the convention? This is positive or this is positive. I don't know. So in any case, so this one has to be 0.12. This here has to be, I don't know which direction it will be going. This will be plus minus 0.1. So you can basically you get all 26 degrees of freedom, you choose the desired position of those 4 degrees of freedom, and then you execute it, and then it should gently move over a little bit. So it's actually not too terrible to I would make steps. Alternatively, you can do something nicer. You just program in the program, which you know how to do. You know how to set a target point for your minimum jerk trajectory by now. And you just make it slowly bigger and bigger and see what happens. And run your program rather than doing this manually typing that drives you nuts at some point, I promise you. Okay? So, let me go back. So you need to observe the red bar on the floor. It will tell you where the center of gravity is. There is a nice little command. Now, task, where is the COG? And it will print it out to you. And there is also another command which I showed you the last time. Just now, task, oops. See where shows you the Cartesian positions of all n effectors. All n effectors are the arms and the legs. In particular, you care about the left and the right foot. And it will tell you what's the center of that thing. So that is going to be, what's happening here? What have I done wrong? Okay, back. What? I don't want these messages. Sorry, my computer just thinks which I don't agree with. Okay. My computer is Okay. This direction. And we are recovered. Okay, so here's where we were. Hopefully everything back. Yes. You can basically do small steps to get over the foot. Don't create conflicts between the legs due to loop dynamics. And if you finally know your target that you basically do incrementally through trial and error, you can then basically program this as the proper target, do a proper minimum jerk movement over there in joint space, and then move one leg up. Moving one leg up will most likely involve the hip flexion extension and the knee flexion extension joint. It could be that you should also move the ankle up and down. And again, you can, well, it depends how you do it. Let's look at the robot from the side. So from the side, you have a body, you have a degree of freedom here, degree of freedom there, and the foot. So if you just swing your leg up, you're going to fall over forward because the leg is heavy. So you need to move it up in a concerted way. So you move this a little bit up, then while you're moving this up, you have to move this a little bit backward. And in order to not hit the ground with your toes, you may have to move this a little bit up as well. And the interesting thing is, if you move this here up by 0.1, and you usually have to do the knee by 0.2, and the ankle again by 0.1. The knee basically has to do twice as much because it has to accommodate the ankle and the hip. Okay, that should make a movement like this. And if you move your leg straight up, the center of gravity should not mess you up. You just want to move it up a little bit. You don't have to get off the ground a lot. That much is enough. But the moment the contact forces are gone, which you see in the simulator, you're fine. If you want, also you can, there's in the now OpenGL process, there's a command which is called coordinate display. In general, the man command works on all of these guys. If you do coordinate displays, it will show you all coordinate systems of the robot, degrees of freedom, and all the names. Just there's so many and it's so compacted, it's actually relatively hard to see. Okay, so that was the one approach how to do things. The second approach, which is the cleaner approach, but it's a little bit more technical, is to move the COG to the center of the foot with inverse kinematics. And I'll tell you for a second how this works. Again, if you do where COG, the print of the COG position. If you do see where, you see the print of where the foot is. This is the target where you want to go. This is your current position. There's a variable, you will see that in your skeleton program, which I will distribute, which tells you the COG position. Then you do a minimum jerk trajectory for the COG position to get from the current position to the target. And you execute it with inverse kinematics, and then you lift the other foot up. So just how does this work in terms of math? The math is actually a little bit more complicated. So here are all the relevant equations. So let me see whether I can get this going without too much confusion. So the center of mass, or the center of gravity in general, is XCOG. Is the sum of the COGs of all individual links weighted by their mass and then normalized by the sum of mass. Okay, so that's the generic definition of a center of gravity. Now, if you want the Jacobian of this thing, well, you just have to do d theta, and you get the Jacobian. That means you get a d theta of this, since the mass is not dependent on the joint angles. It's a constant. Okay, that essentially means what you're getting is something like a weighted sum of the Jacobians of every degree of freedom. So let's look at this again, little picture. Here's my friend the robot. Okay, so every link essentially has its own little center of gravity. Okay, this has its little center of gravity here. I just put them roughly in the middle. You know from the CAD drawings where this is. And it means for each of these points, you can actually compute a Jacobian. It's like a truncated Jacobian. Everything which is in this direction will not contribute to the Jacobian. Okay, so this here is essentially becoming like 1 over sum mi times the sum of mi times the Jacobians of every degree of freedom as a function of theta. So fine, we calculate that for you. You don't have to do that. But this is essentially the COG Jacobian. Now life gets a touch more complicated in these robots, and I'm not touching on this topic of floating-based robots too much, since it's a little bit more technically complicated. Not too terrible, but a little bit. So fine. Normally we were thinking about robots which were anchored to the wall, like this very super simple 2 degree of freedom thing. Now, and this was fixed, that was the world. Now suddenly I basically allow this to be a base coordinate system and put it on 2 legs. So that now it can move. That means the base is actually a very interesting thing. The base of the robot is a 6 degree of freedom system. It was a 6 degree of freedom. It has translation in X, Y, Z, and it has an orientation in alpha, beta, gamma direction, so around the axis. But it has nobody who actuates it. It would be great if you had a puppeteer which could grab it by the butt and just move it along. But we don't have that. The way we think about this in robotics is essentially we think about it as a happy robot floating out in space. It's essentially we now go into kind of space robotics. So the robot is floating out in space, and initially it's just under gravity, and it's like the free space position of the NAO is just somewhere out there floating. And then you basically think, okay, what are the Jacobians we have to deal with now? Well, the Jacobians, when it comes to where my n effectors are the same Jacobians as we're used to. It's a Jacobian relative to the base, but then the base actually adds something to the story. The way now people think about this is they create a new state vector for the robot. Before we just had our joint angles. Now we add the base position and the base orientation. And I just want to do it for orientation. Let's make this alpha, beta, gamma. I'm not telling you anything about whether this is fixed angles or anything like this. That's all base. I don't need to worry about this project. Okay? So we have now a 6 extra degrees of freedom which the base added. Now, fine. And what is, if you now go into the world of Jacobians, we put little dots on these things. And this here becomes a angular velocity, omega base. So this is nicer to work with. Turns out the moment you go into velocity land, angular velocities for the base, essentially they're directly related to quaternions, so you can do math with them very easy. You don't have to do Euler or fixed angles. And there's now a Jacobian, which depends on theta, but also on the base. Let me just write base here, which relates that to the position or the velocity of every end effector. Okay, so this is what is called the floating base Jacobian. It's not very complicated, but the base is actually contributed the positional degrees of freedom. Best you say, well, if my base is moving with a velocity in a particular direction, well, then the velocity of this goes in here and basically directly affects my velocity of the end effector. So very simple. My base is moving forward with 1 meter per second. Guess what? My end effector, my fingertip, is moving forward with 1 meter per second too. Since the two are they're hanging out together. Okay? The same is when we start orienting, basically we start rotating. So I'm rotating with a certain angular velocity. Well, then my fingertip rotates with a certain angular velocity as well. So actually, the base Jacobian is a relatively simple construct. I'm not going to show you exactly how to compute it, but it's actually not very hard. Good. So we now get these kind of new Jacobians, which are floating base Jacobians. And if the floating base Jacobians exist for every n effector, then they exist for every center of gravity of every link, and then they exist as well for the entire center of gravity. It's just adding them up in a weighted way with the weights coming from the mass. Cool. So that gives us a slightly more complicated Jacobian than what you've been used to, but not much more. It's just a little bit bigger. Additional, we need now, and this is coming back to your question, I believe, we need to now insert that we have constraints from the world. And the constraint is that our feet are not moving. So this is very easily expressed by saying that the Jacobian of the left foot times, actually this is the floating base, and I have to make it floating base, times this big vector theta dot x dot base and omega base, well, has to be 0, this multiplication. Since my feet are not permitted to move. Make sense? That's just a constraint equation. Whatever my degrees of freedom are doing, my foot cannot move. So if that is for the left foot, the Jacobian, then it has to be to 0. And the same is obviously true for the right foot. We have the same vector here. Okay? These are constraints. Now, fine. If I have constraints like that, I can basically, the two of them, the two Jacobians, because I have 2 feet, I stack them together. It becomes a bigger Jacobian for both n effector at the same time. Stacking together just means all the rows of the first one come first, and then come all the rows of the second one. So this had 6 rows, and now this has another 6 rows, so I get a 12-row Jacobian. And from this Jacobian, actually, I can compute a null space projector. Okay, we talked about that at some point. That is basically all the movements which can, so this is a constraint. What I'm interested in is all the movements which can basically not violate, or which do not violate the constraint. These movements have to be in the null space of the constraint Jacobian. The null space of the constraint Jacobian, or the projector, I can compute with this pseudo-inverse formula, which you've seen before in the inverse kinematics lecture. And then I create a new Jacobian, which is now the CUG Jacobian, which I had before, multiplied with this constraint. And that basically means everything gets first projected into the feasible space of what the robot can move before the Jacobian is applied. And this is now our new CUG Jacobian, which takes the constraints into account. A little weird, huh? But nice linear algebra. Makes a lot of sense, null spaces in this case. So basically now just me here, I'm doing a null space dance for you. It's pretty cool. You don't get that every day. Good. And then inverse kinematics becomes standard inverse kinematics. Assume you create a desired trajectory for the CUG. And you have to do with your minimum jerk things. It's just an X, Y, Z desired trajectory. Super trivial. And you need the velocity as well. So then you create a very simple reference velocity, which you usually say, so this is my current position of the CUG, that's my desired position. If there's an error, I have a little p gain, which helps me catching up. And then here's my desired velocity from the CUG at all. If I have no error, then the reference velocity is exactly as my desired velocity. There's a little bit of an error that helps me catching up or slowing down, depending whether the error is positive or negative. Okay? This thing I have, and then basically I take this reference velocity, run it through the pseudo-inverse of the CUG, and out I get the desired velocity in joint space, the desired velocity in the base position, and base orientation. Now those I don't need, I can't actuate anyway. So I just happily ignore them. I only care about this thing. So I get a desired velocity in joint space, which I can then, I know the time step of my robot loop running in our world, it's 10 milliseconds, 0.01 seconds. So you integrate the current desired velocity and add it to the current desired position, and that gets your next desired position for your joint space. And that's what you would be executing on the joint space, just with a PD controller. So I'll give you a skeleton program which basically computes this pseudo-inverse for you, so you don't have to worry about that. So all what you would have to do is basically make it a little bit of an inverse kinematics algorithm to get it going. So all this, you can look at the code. It's going to be in the NAO, in prog root NAO, which implements that stuff. It's just a lot of nested for loops, which do matrix multiplications. It's medium pretty. It's just, if it's right, it works. If it's wrong, it doesn't. As simple as that. Okay, so this is the nicer way of doing things. And for this thing, you don't have to twiddle, do anything else. You just move your center of gravity over. You've got to be a little bit careful with this gain. If it's too small, you may drift away and fall over because you get always integration errors, numerical errors. If it's too big, it will explode. Explosions you've already by now, I think, experienced. There's some discussions on the email list about things exploding when you do this kind of rectangular movement. I'll figure out exactly what's going on there. Okay. And that's it. And then basically you get a balance task at CPP today, which is your skeleton, how to basically implement that. It will compute all the complicated inverse kinematics terms. But again, it's up to you. Doing this in joint space should work pretty much with probability 1. It's just a little bit of a twiddling approach to make it work. Doing it with inverse kinematics is much prettier. Then you can do many more things. So you're controlling the right quantity. So it's going to be nice, hopefully. Oops, I didn't want to do that. Let me go back. Okay, that was bad again. Maybe I should practice. As a small aside, so I gave you an inverse kinematic solution here without null space stabilization. Okay, that means we're just controlling how many degrees of freedom do you need to basically move a center of gravity. Well, you need, given that we just do position, we don't care about orientations anyway. So we need somehow 3 degrees of freedom to move. The NAO has 26 degrees of freedom. So that means 23 degrees of freedom are happily doing stuff which we don't know about. So they are in some kind of null space of what matters. In theory, the right thing is to constrain them with a null space projector and basically anchoring them to some kind of a rest posture. We could do that, and if you want to you could implement this as well. I would assume that normally if you just do one movement to the side, it will be fine. A second movement to the other side is fine. If you start moving back and forth, you may start accumulating null space motion, which I have no idea what it's going to do. And you may fall over. So it may drift away in null space. And that, the only way to get rid of that is create a null space component as well. So you can look up in the inverse kinematics lecture. So you will get also the null space projector, I think, of this Jacobian in what we are computing. So you could actually stabilize it. But I think you don't need it if you just do 1 or 2 movements. So don't be, it's very important, okay? Please do not program something complicated. Rule number 1 in all these things, do tiny little, add 1 line of code, so to speak, and see whether it does something useful. Print it out, look at it. To very tiny steps. If you just write cool code and you try to kind of debug it, the robot explodes, fall over, there's all kinds of stuff, you have no idea what you're doing. Do very slow movements initially. There's no need to do a 1 second or a half-second long movement. Just move your booty over very, very slowly and see what happens. And you can actually nicely watch the contact forces in the simulator, or maybe it explodes and does something which we haven't seen yet. Send me email. We're going to fix it. So it's a little experiment. We haven't done something with such a complicated simulator ever before. So you're guinea pigs. Cool. But you get a lot of slack, don't worry. You get advantages for that as well. Good. That's it. Fine, yeah, implementing, it's going to be trivial. Everything will be in the code. I don't write it here. You will have it in this task. There will be all the variables you need. You just read the code. And the code is not going to be much more complicated than what you've currently generated. Even that you don't have to compute the math components, which I just showed you. All right?
So we have 1.5 weeks.
You can take longer, okay? At some point, we have to enter grades in the system. There's no real, if you want to take till mid-May, totally fine. Also, the next homework will give you time. We want to finish that exam. I will send out actually the question catalog today as well. That is our last really harder deadline. That on the 1st of May, we do this exam. Homework 4 and the project, you can trail. Just at some point, we have to enter the grades. In the sense, for the project, at least, I would love to see what you've been doing. If I happen to be not around, then the TAs will be good enough and you show that it's working. You can also create a video, send it to us. But it's I would like to see it on your computer. It would be so much more fun. But your groups now, okay? This is group work for the project, not one individual, although you can also do it by yourselves, whatever you like. Okay? Happy? The answer is yes. Good. Then that's it. Bye-bye.